We saw that in the previous lecture that this equation represent the damped harmonic oscillation, and this equation is a homogeneous linear differential equation of the second order. Now, to solve this equation, let us consider that its solution is x equals to c into e to the power alpha t, where c and alpha are arbitrary constant, and this is equation 4. Now differentiate it equation 4, which gives dx by dt equal to c alpha into e to the power alpha t, and d2x by dt square gives that is double differentiation of this solution. d2x by dt square equals to c into alpha square e to the power alpha t, and use this value in equation 3. So we will get now equation 3. So equation 3 now becomes c into alpha square e to the power alpha t plus 2r into c alpha e to the power alpha t plus omega square c into e to the power alpha t equals to 0. Now taking c into e to the power alpha t common from each term, we get c into e to the power alpha t under bracket alpha square plus 2r alpha plus omega square equal to 0. So equating this value to the 0, because this can't be 0, alpha square plus 2r alpha plus omega square equal to 0. Here we see that this is a quadratic equation in alpha, so we can get its solution by directly using formula, that is alpha equals to minus 2r plus minus under root 4 square minus 4r square minus 4 omega square by 2 from this equation. That is, this is also a quadratic equation. If we equate it to 0, x square plus bx plus c equal to 0, this represents a quadratic equation in x whose solution, that is value of x, comes out to be this. There are two value of x, one we have to take plus and then we have to take negative value. So we have alpha equal to minus r plus minus under root r square minus omega square. So the general solution of equation 3 will be x is equal to c1 e to the power minus r plus under root r square minus omega square into t plus c2 into e to the power minus r minus under root omega r square minus omega r square into t. This is equation 6, and c1 and c2 are arbitrary constant. Now from this general equation, we can consider some condition here. So there are cases we can discuss here. There is case 1 when which is also the case of heavy damping when r square is greater than omega square. Here exponents in this case under root r square minus omega square is real and less than r. Therefore in equation 6, both the exponent, that is minus r plus under root r square minus omega square and minus r minus under root r square minus omega square, are negative. It means that the displacement x of the particle continuously decreases with time. That is, the particle, when once displaced, return to its equilibrium position quite slowly without performing any oscillation. Such a motion is called over damped motion and is shown by this curve, and this can be shown by a pendulum moving in thick coil or by a moving coil galvanometer shunted by a very low resistance. These are the example of heavy damped oscillation, that is a pendulum moving in a thick coil or moving coil galvanometer shunted by a low resistance. Now next case is second case is of critical damping, and in this case 2, when critical damping, when it is r square equals to omega square. So if we put r square equals to omega square in equation 6, that is a solution given by 6 does not satisfies equation 5. Now consider that r square minus omega square is not 0 but a small quantity or given by h. Then the solution x is given by c1 e to the power minus r plus h into t and c2 e to the power minus r minus h into t, and this can be written as equals to e to the power minus rt, c1 e to the power st plus c2 e to the power minus st again. This e to the power st and e to the power minus st can be expanded, so e to the power minus rt, now expanding this value we get c1 under bracket 1 plus ht plus dash 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 and plus c2 1 minus h plus dash 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 dash. So again we have e to the power minus rt and c1 plus c2 plus ht into c1 minus c2, because higher terms has been we have neglected higher terms in this. So finally we get e to the power minus rt equals to a plus bt, that is taking c1 plus c2 as a and c1 minus c2 as b. H into c1 minus c2 as b. So again here we get a equals to c1 plus c2 and b equal to h into c1 minus c2. Now the graph of this equation will be like b, like this. This is the graph of equation B. It is clear that from these graphs that in this case the particle tends to acquire its position of equilibrium much more rapidly than when r square is greater than omega square, that is in the first case. Such a motion is called critically damped motion, and it is often desirable to arrange for critical damping in many pointer instruments so that the pointer moves to the correct position and returns to 0 in the minimum time. Now the third case, which is called light damping. Third case is of case 3, light damping. In this case, r square, we take r square is very less than omega square, and this is the actual case of a damped harmonic oscillator. And in this case, that is in this case, under root r square minus omega square is imaginary. So we have to write it in the imaginary form, that is under root r square minus omega square as j into under root omega square minus r square, where j equals to under root minus 1, and it can also be written as j omega dash. Omega dash is equal to under root omega square minus r square. Now the solution of equation will be written as x equals to c1 e to the power minus r plus j omega dash into t plus c2 into e to the power minus r minus omega j omega dash j into t, or this can be written as e to the power minus rt into c1 e to the power j omega dash t plus c2 e to the power minus j omega dash t. Now we can change it into cos and sine form. So we can write it as e to the power minus rt, and this can be written as cos omega dash t plus sine omega dash t. Complex form of this exponential, that is c1 into cos omega dash t plus j sine omega dash t, and again it can be written as cos omega dash t minus j sine omega dash t. From the De Moivre's theorem, we know that it. So finally it can be written as e to the power minus rt, and solving it, c1 plus c2 into cos omega dash t plus j dash j into c1 minus c2 sine omega dex t Now this equation further may be simplified as, that is taking c1 plus c2 equals to a sine phi and j c1 minus c2 equals to a cos phi. The above equation will become e to the power minus rt and a sine phi cos omega dex t plus a cos phi sine omega dex t. Now this can be further simplified in a trigonometric form. This is the formula for sine c plus d. So will be e to the power minus rt and a into sine omega dex t plus phi because sin c plus sin d बराबर है sin c sin into cos b plus cos a into sin b. So the final solution will be x equals to a into e to the power minus rt sin omega dash t plus phi. So this equation, from this equation, where omega dash, we know that omega dash is equal to under root omega square minus r square, and j is equal to the minus, now here j is absent. So this is the solution of differential equation of the damped harmonic oscillator, and from this we can draw conclusion regarding amplitude, frequency, energy, etc. So first let's see amplitude. The amplitude of the oscillation, is a into e to the power rt, and which is not constant, but instead it decays exponentially with time due to the damping factor e to the power minus rt. This is an under-damped motion and represented by a curve which will be shown later. Now the time interval in which the amplitude of oscillation falls to 1 by e of the its initial value is called the mean lifetime of the oscillator. The mean lifetime comes out to be 1 by r. Mean life comes out to be life equals to 1 by r or 2m by b. So if damping were absent, that is r equals to 0, the mean lifetime would be infinite, that is the amplitude would have remained constant. Now we see the time period, which is given as t equals to 2 pi by omega dash or 2 pi by omega dash is equal to omega square minus r square, and which is slightly greater than 2 pi by omega, that is the period in the absence of damping. So due to damping, the period is slightly increased or the frequency is slightly decreased. The damped frequency is given by damped frequency ft is given by 1 by 2 pi under root omega square minus r square. And where omega is under root k by m, omega is under root k by m, and r is equal to the b by 2m.